Okay, this is a tutorial on visible light spectrum, the lab that we are doing in class, and the equations that you're going to be working out. And here's just an example of visible light. We can see here it starts from red, orange, yellow, green, blue, indigo, and you probably can't see this word here, but it says violet. And the numbers we're going to be working with are the bottom numbers here, the 400 nanometers, 425 nanometers, etc., the nanometers wavelength. Here's a slide that shows you the what a wavelength is. Wavelength is measuring from the top of a wave, one wave, to the top of another wave. And frequency is how many wavelengths you have per unit time. So this first example here is going to be a low frequency, and the bottom will be a high frequency. Okay, and if we look at our light waves, red is a very long wavelength. It's a low frequency, and violet light is a very short frequency. Here are some of the variables and constants that we're going to be working with, and you need to write these down. So I'm going to pause here, give you a few minutes to write these down. Okay, our first variable is F, and that stands for the frequency, and the units are hertz or 1 over S. It's the same thing. Then our next variable is the lowercase lambda, the Greek letter, and that's the wavelength, and that's measured in nanometers. If we go back and look, we see here they're all measured in nanometers. Next, H is Planck's constant, and that is a constant number. This never changes. You can find this number in your reference materials, that handout that I gave you. C is the speed of light, and again, that's a constant. That's something that never changes, so you'll just look that up on your reference materials. The thing we need to keep in mind that all units need to be the same. So the only unit that we need to be mindful of is the wavelength. The nanometers here, that has to be in meters, because the speed of light is measured in meters per second. So that's going to be our first step. If it's not, and here's a hint, if the wavelength is not in scientific notation, then it's not been converted to meters yet, and you must do so. And here are our three equations, and these are found on your reference materials, so you don't have to memorize these, but you do have to know where they are in the reference sheet. Alright, so let's work out an example. Green light. When we see green light, it's because electrons in an atom, when you put energy into that, like when we are using fire, we're adding all this energy from the fire into the toothpick, and we're seeing green light. The electrons that are in that chemical, that element, absorb that energy, and they actually jump to the next higher shell. And when they lose that energy and the electrons fall back to their ground state, to their normal shells, then they release photons, and these photons we pick up as light, and so that's where we get light. So on step number 1, we're converting the wavelength of that 550 nanometer green light into meters, and here's our conversion factor. So we set it up like this. The 550 nanometers goes on top over 1. We want to get rid of nanometers, so we put it here on the bottom. We're going to meters, so that goes on top. Then we put in our conversions. 10 to the 9th goes with nanometers. 1 goes with meters. So nanometers cancels nanometers. And when you divide this out, you get 5.5 times 10 to the negative 7th meters. And that's going to be our wavelength. So what we do then is we find the frequency of the light using this equation, and we rearrange it to solve for frequency. So we divide both sides by lambda. So you're going to get the equation F is equal to C over lambda. And then we're just going to simply substitute in a value for C and a value for wavelength. Well, if you remember, C is a constant. We get that off of our reference sheet. So that's 3.0 times 10 to the 8th meters per second. Then we substitute in for lambda the wavelength, which we converted here. So 5.5 times 10 to the negative 7th meters. And then when we divide that out, we get 5.5 times 10 to the 14th. And the units is 1 over S. The meters cancels. So it's 1 over S, or hertz. And since we have now a frequency, we substitute that in to this equation to get energy. Okay, now H, if you'll remember, is a constant. That's on your reference material. So that's 6.63 times 10 to the negative 34th joules seconds. And then the frequency we just calculated, we substitute that in. 5.5 times 10 to the 14th, 1 over seconds. And we have to use 1 over seconds here instead of hertz, because this is joules seconds, and we want the seconds to cancel. So when we multiply that out, we get 3.65 times 10 to the negative 19th, and the seconds cancels, so we're left with just joules as our energy.